In this video, uh, I will explain how I created a RAG functionalities and deploy into EMR. So basically, we had a task of, so we had an input of more than 600 PDFs. So our task was to create an index from the input PDFs in a MapReduce form. Basically, parallelly, we have to create the indexes for all the PDFs. Then our task was to get the stats about those PDFs like vocab count and similarity search on that PDF on those PDFs. So uh, I developed the Scala application and I uploaded the jar into S3, and then I created this EMR cluster, and then I ran the Hadoop jobs on this EMR cluster. So let's see how I created the cluster and how I ran the jobs there. So first of all, I selected the application bundle for Hadoop because our all the code in Scala basically it uses Hadoop's APIs and does the MapReduce. Then this is the important part. Basically, EMR provides us three nodes: primary, core, and task. So prime nodes basically runs the master nodes, that it runs a name node. So it basically contains all the metadata about the Hadoop cluster. And the core and task node will do the actual map reduce thing and all the compute thing. So here it's important to get a appropriate size because it depends upon your job. So I did M5 2x large, so it gives me 32 GBs of virtual memory and 32 GBs of RAM and 8 core. So for all this primary core and task, I did the same configurations. Then EBS root volume, I let it be default. So this is important. So instance size, so it shows like how many instances you want to use. So it depends on upon your job and the instance size. So mine is pretty good, like 32 GB. So I didn't need too much instances. Also, to be more economical, I choose to go with one each. And then I had a this bootstrap actions. So this is important. So in this uh, script file, defined all the commands, all the things that I wanted to install into my EC2 container whenever EMR would boot for the first time. So for example, it would, this script file would contain like to command to install Java, commands to, because we would be making indexes, so commands to install Ollama APIs, Ollama embedding APIs. So and so all those commands, the bootstrapping commands, like all the pre-installed software that we need in our system, so we can define it into this bootstrap script file. Then this is a EC2 key pair I created to SSH into my cluster. So then I created a new service role for my EMR and EC2 cluster, and I gave, for now, because this is just a homework, I gave permission to all the S3 buckets with read and write access. And I clicked on create cluster. So it basically would create the cluster. So since I have already uh, run this job once, so since I have already run this job once, I would just show you how the logs look and how the things look in the Hadoop. So basically here I have uh, logged in SSH into the master node of the EMR cluster. So first of all, I copied my jar file. So this jar file contains all the code for MapReduce. So I copied this jar file into this EC2 instance. So you can see this. This is the jar file I had deployed. This is one big fat jar that I deployed into S3. So I have copied that, and after this, just we have to, because EMR will automatically take care of all the things. We just have to give command and the jar file. So Hadoop command will basically run this all the jobs for this file or for this jar file. So what I have given is first argument is this jar file, then the driver classes, then rag. So this is important. So we have multiple, as you know, we have under this homework we had multiple mappers and reducers. So we had to build multiple mapper and reducer. So this is rag mapper. So in the command line, I can define what mapper, what job I want to run. So basically, what this rag means is we have defined multiple mappers in our driver code. This is the main class. So we have defined multiple mappers. So it will call the appropriate mappers according to this argument. So the rag means like it will, this is the main mapper reducer for the indexing jobs. So basically we have uh, all the PDFs. So to create the indexes out of those PDFs, so I use this rag mapper. So for that I have to first give the input path. So this path dot text, this is parent in the S3 file. So if you see this path, this contain all the paths to the PDFs. So it line by line it contains all the paths to the PDF. Then I give the output path. It is also the this path will basically contains all the indexes, all the sharded indexes in this path. Then I give the model name, embedding model name into the argument. So nothing is hard coded. Everything I have given through this command line, and then the similarity. So for now I've used cosine similarity. So I can also give in this arguments the how many mappers and reducer I want to use. So that is also configurable. For now, for the default value, I have used 13 mappers. So each mapper would approximately get around like 50 PDFs. So 13 mappers and 8 reducers for default if we don't give any value here. So we can change that accordingly. So once I run this command, you can see I have logged that it will run in a mode is equal to rag. It means that it will run the rag MapReduce job. So first of all, you can see here the number of splits is equal to 13. It means like total 13 mappers would be there. So it has, because I have used line mappers, so it will so they are like 600 lines, because it basically these are paths. So these are paths, so there are like 1600 lines. So it will, the each mapper will split. So like if there are 13 mappers, each mapper will split this file around like 50 files will go to one mapper. So that's that. And then I this job ran, so it took quite a few time. So I got like, it took some time so to see the logs for this job. I can search here. So this was a job that ran, and here you can see why using this command yarn application list. So basically this will yarn will list all the jobs that it ran. So you can see this job ID, this it finished and it succeeded. So you, the output for this was in this output folder. You can see that I created 8 reducers. So each reducer created one index shard. So this any one of these shards contain all the indexing for some number of documents. So these are the 8 indexes that got formed. So this was one of the jobs. The other job was to basically uh, get the statistics of from all the documents. So stats means like to get the word counts and to get the similarities between words and to get the analogies between words pairs. For that also I created a job. So let me see where I ran that command. Yeah. So here you can see Again, I copied the jar. I removed it because of some issues I had with it. So I again copied it, and then uh, you can see there is like this word stats. So I have this is a second job, MapReduce job. This is the second job I have written, MapReduce job, word stats. So basically, in this, the mapper will basically take individual tokens and it will basically emit the counts and um, the for each token the embeddings, and reducer will combine all those same tokens and will do rest of the calculations. And so here, just on the only difference was I just changed the name of the job here. The difference between the previous command and this command is just I name the change the name of the job, which is word stats now. So rest of the things are same. The embedding is same, cosine is same, and mapper size and reducer size is again same, which is default. So again, this did 13 splits. Basically 50 around 50 PDFs went to one mapper, and then it ran, and basically it was not a quite it was not that big. So this job only took around like for an hour, less than hour I would say, because the previous one took around like 3 4 hours. So this completed, and it all the outputs were in are in this output file here. So this S3 contains all the CSV files that got generated, like nearest neighbors and similar analogy. So I have downloaded them all into my local, and I want to show you what how they look. So this is the first file merged. So basically it contains the count and embeddings and token IDs. So basically count, so like a bait word is 16 times, a byte is 5 times, and also it contains the embeddings for that word. So this is the embedding vector. So it is like it is 1024 dimension vector, I guess. So yeah, this contains tokens, the word counts, and the embedding. So like accuracy has come 25 times. So this is huge file. Like it contains around like 70,000, I think, records. So this is huge. It won't end. So yeah, it contains around like more than 75, like around 74,000 tokens. I don't remember the exact number. Yeah, the other file was oh, that's the same file. Yeah, other file is uh, this nearest neighbors CSV. So this is interesting file. So basically, it uh, has all the uh, tokens which are similar to the given word. So like incident is the neighbor is incidents. So similarity scores. It also contains a similarity scores which I have computed. An incident is also similar to occurred. The similarity is 0.883%. Similarly, occurred and accident happened. So all these are the top five similarity words. So I have given that I want to get the top five similarity words. So similarly, like comply, so complying, compliant, obey. So are these are the all the top five similarities that we have got from embedding vectors by doing operations on them. So similarly, breaks, you can see like the similar word for breaks, like similarly like forgotten, neglected, or forgot. So like those are the words. The other stat was to get the similar pairs. So like how the consign similarity between similar pairs. So like this is just I produced for only few number of tokens, like five here. But the one more thing, like nearest neighbors, this is generated for all the tokens, like all the 75,000 tokens. So all that for all those tokens, this nearest neighbors are generated. So yeah, and the next one is analogy pairs. So this is also interesting. So analogy pairs is basically king minus man plus woman equal to. So like my vocab list contains city, country, and Paris and Amsterdam. So what I did was like city minus country plus Paris. So that would equal to Amsterdam. So according to the that cosine similarity rules. So similarly, like love minus hate plus good is equal to nice. So that's that. Then yeah, these were all the stats that I generated. After that, I also created an API. So I have also created a functionality to query the index database so and get the appropriate response. So I have created a API for that. So I just ran that API in the same instance. So basically, what's happening is I queried like what is this like seasonal decomposition data, time series data analysis to Travis, uh, just a curl command, and this query I've got from this PDF which I was shared, which was shared by the professor. So uh, this is a PDF about this seasonal decomposition time series analysis to Travis torrent data. So I just wanted to know more about that. So I just put that and so basically what this does is this does a this also query do a parallel map reduce job on the sharded index. So like we have 8 index, so this will parallelly search on all the 8 indexes and give us top 5k results, and mapper would do that and reducer would combine those results and give us one unified result. So this query is basically this is the query question and this is the answer that we got. So till this point this is the answer. So the provided papers demonstrate how time series analysis is applied to the tariff data, and this the analysis confirm this is this. So this is in so this is the answer that we got till here. And that this is the interesting part. This shows like from which PDF did we get the answers and from which chunk. So it also mentions like we got the answer from this PDF chunk 9, the same PDF chunk 0, and the same PDF chunk 5, 8, and so on. And in the results you can also see the score basically. So if I search score here, so you can see score of 92%, like 0.92, and it shows like which chunk produced this score. So it basically in the increasing order of scores it displays the answer. Similarly the next score we can see 91%. So it also gives, so basically all this is context. So it tells us like from this context I got this score and this is the context I read. So that's how the rag works here. So that's all about my project. So yeah, this completes my demonstration. So basically it had three parts. One was to parallelly create indexes and store into this S3, and the second part was to create a statistics. So for that also we had a job and statistics and the similarities between the tokens. Then third was to create a to search the shards parallelly and give the results to the input query. So yeah, that's conclude my presentation. Thank you.